We are OroValle, a mining company that extracts and processes ore in Asturias, northern Spain, producing gold, silver, and copper. We belong to OroValle Minerals Corporation, a Canadian company listed on the Toronto Stock Exchange under the symbol ORV. Our activity takes place in the Boinas and Carles mines, which are 30 kilometers apart. Both were mined as open pits in the early 2000s, and now both are mined underground. Additionally, OroValle carries out continuous geological exploration work in the 3 gold belt areas of Asturias in search of mineral resources for new and continuous operations. OroValle manages a land package of 23,000 hectares in granted mining rights, plus 22,000 hectares in progress. We are committed to sustainable mining that balances safety with zero accidents, environmental care, the well-being of the community, and the economic results proper of a private concern. Safety is the key priority for all the operational processes at OroValle. A strong safety training program is in continuous improvement. OroValle is committed to the development of Asturias, generating employment, synergies with local partners, and the multiplier effect of indirect economic activities. Our company has a workforce close to 600 people, including direct employees and contractors, and generates more than 2,000 indirect jobs. Since its inception, the company has invested close to 160 million euros. In Boinas, we mine 2 types of mineral. The first one is skarn ore, formed by metamorphism when igneous bodies with an approximate age of 300 million years come into contact with limestone, forming metamorphic rocks with a concentrated mineralization, gold, silver, and copper. The second is an oxide ore. After the skarn generation phase, other later epithermal type formations arose, related to faults to become oxidized and formed supergenic alterations, causing gold enrichment. There were also remobilization phases that further enriched the mineralization. Access to the Boinas mine entrance is at 400 meters above sea level, the deepest level being 0. The most important infrastructure is a vertical extraction shaft and hoist, 400 meters deep, which has a vertical fan and air systems with airflow at 170 cubic meters per hour, and a main transport ramp with a 5 meter by 5 meter section. Boinas has 2 zones differentiated by mining method: cut and fill and sublevel stopping. The average monthly progress in underground galleries is 500 meters with drilling and blasting in hard terrain and 750 meters in weaker rock terrain, which requires retro excavation. The daily extraction by the hoist is 700 tons, which adds to the 1,400 tons per day hauled out by trucks. All maintenance services are located close to the mine portal. Once equipped with their self-rescue gear, mining lamp, mask, goggles, and gloves, the shift crew proceeds to the dating meeting room. This room is divided into 3 functional groups: transportation, jumbo development, and mechanical advance. It is here where we find the boards with safety information, work planning in the mine, maintenance information, and the work of the service teams. In this room, the work team receives a safety talk with messages on safety regulations, lessons learned from incidents and accidents that have occurred. At the end of the safety talk, each shift supervisor gives the work fronts, tasks, and specific equipment information to his staff. With all this received information, the shift crew is then distributed throughout the underground mine. Development in cut and fill is carried out with retro excavators equipped with hydraulic hammers. These machines advance 1.5 meters in length throughout the section. Previously, the face has been reviewed and marked by the shift bosses. Marking consists of following the direction and gradients guidelines on the face set by the surveying personnel. Once the 1.5 meter advance has been cut, a low-profile scoop cleans up the material from the face. The material that is generated with each 1.5 meters is around 60 tons. The scoop loads the material into trucks. Once the face has been cleared of rubble and is free of material, a shotcrete robot is put to work at the face. Its function is to stabilize the ground with the projection of at least 10 centimeter thick layer of shotcrete. The shotcrete is produced at a plant outside the mine. The engineering department develops specific formulas of shotcrete to be used. Once the shotcrete is produced, it is transferred to the concrete mixer vehicle, which will transport it to the production areas of the mine. When the mixer reaches the face, it unloads the shotcrete into the robot hopper. Prior to projecting the shotcrete, the face will be reviewed by qualified personnel, validating its good condition and giving permission to start the spraying. The operator uses markers to ensure the thickness of the shotcrete. Once the face has been sprayed, a 2-hour wait is necessary for the shotcrete to set. After setting, it is mechanically supported using a roof bolter. Following a design established by the geotechnical department. Subsequently, they insert a 2.4 meter long Swellex into the drilled holes, 40 per advance, which will then be inflated to 300 bars of pressure. In this way, the terrain is further stabilized. On average, one rock face is reinforced every 2 advances, that is, every 3 meters. The production process within the sublevel stope areas is divided into 2 processes, advance and stope. Advanced drilling is carried out with jumbo drill rigs. These jumbos drill 45 millimeter diameter holes, raised bore to 112 millimeters, and 4 meters in length. In OroValle, there are several drilling designs, depending on the type of ground. They range from 54 holes to 64 per face. Once the face is drilled, it is ready to be charged with explosives. This work is carried out by the gunners, who review the drilling design carried out at the face and extract the necessary amount of explosive from the magazine. Once in the mine, with the help of a telescopic handling device, they proceed to load the drilled holes with explosive. On average, 200 kilograms of explosive are used per blast, enabling an advance of around 3.7 meters per event. At the end of the shift, with the approval of the shift supervisors, and with nobody remaining inside the mine, the loaded rock faces are fired. After the blast, and once the gases generated are dissipated, the state of the face is checked. Then a scoop shovels up the blasted material, 120 tons on average, into trucks. Faces, already cleared of rubble, must be scaled, a task carried out by retro-excavators with hydraulic hammers. This mechanized scaling is carried out to eliminate the rocks that were not detached by the blasting, and it is mechanically reinforced with face drilling with a jumbo. The jumbo drills 43 millimeter diameter holes in the gables and roof, following a pattern established by the geotechnical department. Subsequently, a 2.4 meter long bolt, split set, is inserted in each hole. Jumbo development faces are secured with each advance with 30 split sets and mesh according to the defined standard. Once the top sill and the bottom sill galleries have been made, the work to mine the stopes can begin. For each production stope, the engineering department designs the specific cable support. Long hole production drill rig drills 70 millimeter diameter holes with lengths between 6 and 12 meters, depending on the design. Once the holes are drilled, the cables are placed and cemented, and after 24 hours for the cement to set, they are tightened. With the cable support completed, the production holes are drilled. This drilling, just as the cable drilling, is carried out using the long hole production drill rig. The holes are drilled with a diameter of 89 millimeters, raised bore to 152 millimeters, and with lengths ranging from 10 to 25 meters, depending on the design of each stope. Once part of the production drilling is done, the drilled holes in the stope are fired sequentially to begin extracting ore. The loading of the production blasts is carried out based on the defined plan, with the theoretical and actual data from the drilling. Electronic detonators are used for stope sequences. After loading, the area is beaconed off. At the end of each of the 3 daily shifts, and with all personnel out of the mine, except gunners, the blast is fired. Once the blast gases have dissipated, the stope is checked, and with the approval of the supervisor, the mineral is extracted. The scoop intended for this task has remote control to greater operator safety. This material is then loaded onto trucks. There are 2 systems to transport material to the surface, by way of the shaft hoist or by truck. The extraction through the shaft is only for hard rock skarn, which in turn can be ore or waste rock. The trucks, loaded at the rock faces, transport the material to the shaft, unloading it into the bulk chute. Next to the chute there is an arm with a hydraulic hammer that helps to reduce the volume of the material deposited by the trucks. This material falls into a crusher. Then it is grinded down to a suitable size to be extracted through the shaft. A magnetic separator divides the iron, bolts, cables, from the material to be extracted. This belt empties the material onto the fines hopper, which later distributes the material onto 2 belts, which end up being unloaded into the 2 skips that take the material up and outside. Each skip carries a load of 6 tons. Finally, a belt takes the material to the plant stockpile. The material that is not extracted by way of the shaft is transported by trucks and stockpiled outside. At the mine portal, the material is sampled and then transported to the plant stockpile. This mineral will be weighed and its origin identified. The waste material is transported to the screening area for later use in the production of cemented rock backfill. 2 types of truck operate in Boynas: 24-ton articulated haulers and 15-ton mine trucks. Both trucks are used to transport cemented rock backfill to stopes and galleries. Once a gallery or stope is mined, it is filled. Depending on whether it is of primary or secondary type, it will be backfilled with cemented rock or waste rock, respectively. The process is the same for both types of backfill material. The primary galleries are backfilled with cemented rock. This material, which is transported from the cement mixing zone, was previously screened to obtain the specific grading. Cemented rock is made up of 4% cement mix and previously screened rock. The mixing area is near the mine stockpile, from where the mixture is transported by trucks to the stockpiles inside the mine. The scoops take over from there and transport it to the stopes or galleries to be filled. Cemented rock allows us to safely mine secondary stopes or galleries and thus extract all the mineralized rock. The geotechnical department keeps track of this process. The waste rock backfilling process is similar to that with cemented rock. The difference is the origin of the material. The waste rock comes from the advances in faces. The installation of services and infrastructure is a vital auxiliary task at the mine. These accompany the development of the mine, supplying water, energy, and ventilation. All essential for safe and efficient mining. Water and ventilation are supplied through pipes that run throughout a large part of the galleries. Ventilation is brought to the work faces through 0.8 to 1.2 meter diameter mine ventilation ducting. Energy is supplied by transformation centers. In addition to these services, there is an extensive water pumping network at the mine, divided between operations water and clean water. All the water is redirected to the pumping area at 100 meter level, where there are 2 pools, operations water and clean water. The operations water is subsequently pumped outside for treatment. The extracted ore is taken to the treatment plant. OroValle plant has a treatment capacity of 95 dry tons per hour. Ore grades, as well as recoveries, vary according to the blend of skarn and oxide ore treated. The different treatment circuits in the plant permit producing the following marketable processing outputs: copper concentrate, gravimetric door, and leaching door. In OroValle, copper is present in two ways: native copper and sulfide copper, bornite, chalcopyrite, recovered by means of a gravimetry circuit, native copper, and a flotation circuit for sulfide copper and native copper that may remain after gravimetrics. The mineral is classified in stockpiles according to its gold and copper grades. Penalty elements are also monitored at this stage. Once all factors are considered, the stockpiles are fed to the plant following optimal blends. The first process in the plant is dry grinding to 153 millimeters. After crushing, the mineral is subjected to fine grinding at around 74 microns to liberate native gold. This grinding is carried out with water in two stages, a ball mill and a sag mill. The ground ore passes through a battery of hydrocyclones with a diameter of 74 microns. Hydrocyclones separate the ground ore into two streams: spillover or fines smaller than 74 microns and sunk coarse sand with a size greater than 74 microns. Part of the sunk is returned directly to the grinding circuit. The remainder is passed through a 2 mm mesh screen. Ore caught in the mesh is returned to the grinding circuit. The rest enters the gravimetric circuit. This circuit allows the extraction of native metal concentrates, copper and coarse gold, based on their specific weights. In this circuit, a copper concentrate with a high gold grade is obtained. It undergoes a final transformation in the ILEX circuit afterwards. The ILEX circuit consists of a reactor, an electrolyte tank, and two electrolyte cells. The high-grade gravimetric concentrates enter the reactor, to which a mixture of fresh water, caustic soda, and cyanide is added. The cyanide dissolves the gold present in these concentrates. The solution, when charged, is separated from the solid residue by decantation. The solid material returns to the ball mill, and the liquid is sent to electrolysis, where the gold is turned into solid state in the form of a slurry. This slurry is finally smelted to obtain the gravimetric bullion. The overflow from the cyclones goes to the flotation circuit. Here, two types of reagents are added: foaming agents and collectors, to trap copper sulfides on the surface of the air bubbles present in the mixture, which spill over through the cells in the form of concentrated foam. The foam is subjected to a thickening and subsequent draining process with a filter press to lower the humidity to 10 to 12%. This is how we obtain the copper concentrate. The residual pulp from the flotation circuit, after passing through a thickener, is subjected to the SIL process of gold leaching and subsequent absorption into activated carbon. The fine gold particles that do not come out through the gravimetric process or by the physical-chemical flotation process are extracted here by chemical reaction with oxygen and cyanide in the SIL circuit. The carbon charged with gold goes to the elution process, from which free carbon and a gold cyanide complex called electrolyte are obtained. The freed carbon goes back to the SIL circuit. The electrolyte passes through electrolysis cells and generates a cathodic sludge, which is dried and mixed with the appropriate amounts of fluxes. This mixture goes to the melting furnace to obtain the SIL bullion. The final decontaminated waste is deposited in the tailings storage facility. After viewing the process from a broad perspective, the question arises, why such a distribution of metallurgical processes in our OroValle plant? The answer is that Boinas has three types of gold and copper: native, oxidized, and sulfidic, and trying to recover those two metals from a blend of native, oxidized, and sulfidic minerals is a challenging endeavor. The OroValle laboratory is ISO 9001 certified. It is located near the plant facilities and analyzes the following types of samples. Samples from OroValle plant. They are taken from different circuits of the plant and transported to the laboratory twice a day. Grade control samples. These are samples from the mine rock faces of the extracted ore. Exploration samples. obtained from exploration core logs, environmental samples for the control of water in the mine and surrounding area, samples of the final products for sale, bullions or doré bars, and copper concentrate. In this case, certificates of analysis are issued that must accompany our products from the moment they leave OroValle plant to their final destination. The samples first go through a technical preparation according to each type, where following different procedures, they are dried and ground to a particle size of less than 0.075 millimeters and are reduced to a weight of 150 grams without losing their capacity to be a good proxy for the whole sampling material being aside. Then they go to the laboratory where, following two procedures known as fire assay and acid digestion, they disintegrate and remain in solution. Finally, in the dissolved liquid samples, the content of metals of value such as gold, silver, and copper can be measured. These measurements are made using optical spectroscopic analysis equipment, atomic absorption, and ICP. As a general rule, in each sample we analyze between 7 and 12 different chemical elements. To define the mineral resources of the OroValle deposits, lithological information is needed. This is obtained by drilling boreholes to take core samples. Once drilled, the core sample is stored in boxes for testing at a later date. The drill holes can deviate from the initially planned trajectory. Given the importance of knowing exactly where the mineralization is, measurements of these deviations are made using the maxibor. Maxibor is an optical instrument that is not affected by the presence of magnetic minerals that may be present in the deposit. The information obtained is entered into a database. The core samples obtained are taken to the testing area, where a lithological and geotechnical description is made. The different lithologies are described by means of detailed logging. Information is collected on lithological contacts, orientations, and bands, which will later be used in the geological interpretation of them. The geotechnical description is used to define the RMR and RQD parameters that determine the type of support to be used during mining. Afterwards, the mineralized parts of the core samples are prepared for subsequent analysis in the OroValle laboratory. The sample preparation and analysis process is carried out according to international standards. The geological research consists of the integration of the geological and geotechnical descriptions with the analytical data from the laboratory. 13 mineralized bodies have been defined in Boinas and 6 in Carles, just by taking core sample views or sections and vertical plant views, plus making use of the aforementioned lithological information and software applications. Core sample drilling or boreholes have several purposes. Infill drilling, to transform inferred resources into measured or indicated resources. Grade control, to define with greater certainty the grades of stopes or panels in the mining process. Exploration drilling, to find new resources in undefined areas which allow the life of the deposit to be extended. Lithological and geotechnical descriptions are made about the rock faces as the mine galleries and stopes are advancing. There is also systematic sampling in the advances. All this information is integrated into the database using RecMin software. Once the drilling information has been integrated with the samples from the advanced faces, the different mineralized bodies are modeled in 3 dimensions using DataMine software. Geostatistical calculations are applied to the mineralized bodies already modeled, taking into account parameters such as distribution of the grade in the body, the number of samples, length of the samples, and spacing between drill holes. This application results in a model that predicts the distribution of the mineral within the body. The information in this model is what the engineering department uses to design mining operations. Regarding greenfield exploration, OroValle has investigation permits in 3 gold belts in Asturias. The first phase of the fieldwork consists of general geological mapping and the collection of outcrop samples for analysis. Soil geochemistry and geophysical studies can also be carried out. All these studies make it possible to define areas with potential interest, to which more detailed cartography will be carried out, and more samples and prospecting will also be done. The final step is drilling, which will define the mineral potential of the area under exploration. The engineering department defines the mining strategy once the geology data has been received. To do this, it takes into account the price of metals in addition to other factors. It is divided into different areas. Long-term is where geology information is received as block models. Mining designs are applied to these block models that end up quantifying the reserves of the mineralized area in question. For this, it takes into account both the infrastructure of the mine and the key performance indicators of the operation. OroValle uses Deswik and DataMine as software. Short-term performs quarterly, monthly, and weekly planning using the Deswik software sequencer. This planning is coordinated with geology, mine operations, and mine maintenance. Geotechnical carries out the stability study of the different stopes, Stope Atlas, and galleries using DIPS and unwedged software. Additionally, it carries out daily monitoring of the working areas, making sustainability recommendations according to the standards defined in Boinas and Carles. Drilling and blasting carries out the design of the blasting in stopes, for which it uses geological and geotechnical information. They use DataMine's Aegis software. They carry out and supervise drilling for blasting designs and adapt the quantity and sequence of the explosives for each blast. After a stope has been emptied, a reconciliation takes place. Ventilation and Services uses the VentSim mine ventilation software, which simulates the state of ventilation, ensuring established standards for work fronts. They plan and supervise the distribution of mine services, such as air, water, and electricity. Topography is in charge of carrying out the topographic control of the entire operation, both underground and outside the mine. They use Total Station, CMS, GPS, and a drone. Measurements in the mine are carried out with Total Station, which marks and controls all the galleries defined by engineering and carries out a study of over-excavation, sub-excavation. The measurement of stopes is carried out with a CMS, which, once the wireframe of the measurement has been processed and generated, is passed to drilling and blasting for further treatment. The maintenance team is made up of our own engineers, mechanics, and electricians, as well as specialized technicians from Epiroc, Sandvik, Volvo, or Putzmeister. The maintenance planning department, together with the different section heads, designs the maintenance schedule, programs interventions on each machine, and develops and defines KPIs. It is also here where the implemented actions are monitored along with the KPIs, and improvement proposals are made. Close to the mine, we find the maintenance workshops for mobile equipment, infrastructures, pumps, and light vehicles. All maintenance tasks are carried out here to support day-to-day operations. OroValle has other workshops further away from the mine, where planned corrective maintenance operations and overhauls are carried out. In the vicinity of the mine, we find the electrical workshop, where, in addition to carrying out routine repairs for the mobile fleet, are all the other electrical and communications infrastructure repairs. OroValle, in compliance with its duties, environmental steward of its surroundings, and as per our plan, monitors the quality of emissions into the atmosphere and inland water, the latter in the public hydraulic domain. The state of the air masses is monitored by means of measurements in the main emission sources of the plant. Water is monitored by means of programmed samplings. The reverse osmosis plant is located in the vicinity of the mine portal, where mine operations water is treated. OroValle has a complete ecological restoration plan with ongoing revegetation and repopulation of native tree species. The tailings storage facility is located in a former open-pit mine, granting the benefit of not needing a dike to contain the tailings. OroValle is one step ahead in safety, exploration, infrastructure, and personal training to assure a future way beyond its known reserves.